Right, thank you, David. Let's move on to the third talk of the sessions. Sorry for delaying this. Both the speakers had to leave and couldn't be part of the discussion, so that's why we chose to take questions. I hope, Negin, you didn't mind.
Don't worry about that.
So, yeah, without further ado, let's have Negin from the Sloan School of Management at MIT talk about her work on online markets.
Thank you so much, Shipra. So first and foremost, I want to thank the organizer and in particular Shipra for the invitation, and thank you guys for attending the talk. Today, I'm going to talk about online learning with offline greedy via offline greedy algorithms, and I'm going to talk about some of the application in market design and optimization that fit our framework. And this is a joint work with my great co-authors, Rod and Joshua, my PhD student, Francisco Susan, and Ashlyn. Okay, so I'm gonna start with motivating this work. Can you guys see the second slide? I think that there's a lag. No?
We cannot see the second slide yet. I cannot, at least. I don't know about others.
Okay, I think, yeah, I think that you guys cannot see it. I don't know exactly why. So let me stop share and start sharing again because there might be some issue. Okay, so hopefully you can see it now. Can you?
Yes.
Perfect.
Yeah.
Okay. So then, I'm going to talk about, let me motivate this work and by talking about decision-making marketplaces. So if you think about marketplaces, they have to make certain decisions repeatedly over time. So think about online retail stores. For them, like on a regular basis, they have to decide about what items they want to offer to customers in order, for example, to maximize their market share. So another example is product ranking, that in product ranking, we want to, the problem is that how we are going to display the products on online platforms in order, for example, to maximize consumer engagement. And it turns out this is an important problem for the online platforms because as a human, we tend to look at the products that are more visible to us. And as a result, how and in what order products are being displayed is going to influence the customer's decision. And as another example, we have reserve price optimization. So think about running second price auction in display advertising market to sell ads. And in that scenario, one of the important parameters that needs to be optimized in order to maximize revenue is reserve prices. So for all of these problems, we face a few like fundamental challenges. So the first challenge is that in these decision-making processes, we have a lot of uncertainties. So think about assortment planning. As a retailer, I don't know the customer's demand in advance. So for product ranking, I don't know how patient the customers are going to be and how many products they end up looking at to make a purchase. And then for reserve price optimization, I don't know the advertiser willingness to pay. And on top of that, the environment under which the underlying environment under which I'm making a decision can be time varying. So for assortment planning, demand can change over time. So maybe before COVID, people had the different demand function, and now after COVID, people are actually are interested in buying different things. And for product ranking, the same thing. There may be customers before COVID would like to spend more time on online platforms, did not mind actually spending a lot of time browsing, but then after COVID, maybe they'll get busier. And for reserve price optimization, we have similar challenge. But these two challenges are not the only challenges that marketplaces face. There's another important challenge, and maybe the most important challenge here is that let's assume that I don't have any uncertainty whatsoever. Then the underlying offline problems that we need to solve in these decision-making processes is going to be NP hard to solve. So roughly speaking, this is the case because I have too many options to try. So when I'm offering assortment planning, my options is the number of sets that can be like exponentially large. So given these motivating examples and given these main challenges, here are two main research questions. We want to understand how to design learning algorithm for such combinatorial and time-varying environments. And in particular, we want to know if we can transform offline algorithms to the online algorithm with sublinear approximate regret. Can we transform offline algorithms to get good learning algorithms? And the answer to this question, and based on this work, is that yes. Otherwise, I wouldn't talk about it. So the answer is yes, because for a large class of offline problems that admit a robust greedy algorithm with constant approximation factor, we are going to be able to do this transformation. And in fact, for all of these three examples that I talk about, there exists a greedy algorithm, and all of these greedy algorithms are robust. And I'm going to explain what we mean by being robust. And also they give us constant approximation factor. So in the rest of the talk, what I'm going to do, I'm going to use assortment planning as the running example to illustrate our technique. But then our technique can be applied for the other examples that I talk about, product ranking and reserve price optimization. Okay, so let me start with preliminary. And I'm going to walk you through the offline problem. And remember that my focus right now is going to be on just simply assortment planning. So what's the problem? I have n products, and my goal is to choose set S with cardinality at most k that maximizes market share, which is just simply the probability of purchase. And I'm going to use this f of s to denote the market share or the demand under set S. And for many, I think for those of you who know about choice modeling, so for all random utility choice model, this f function is simply a monotone and submodular function. So as a result, my offline problem can be simply maximizing a monotone submodular function with cardinality constraint. So this is the offline problem that I have here. And then the offline problem admits a greedy algorithm with approximation factor of 1 minus 1 over e. And this is I'm sure that most of you know about this result. Is a classic result by Namhasar et al. That they design a greedy algorithm with this approximation factor. But let me walk you through this algorithm, because later I'm going to build intuition based on this greedy algorithm. So the way that this greedy algorithm works is that it has k subproblems. At every subproblem is going to choose a product zi that maximizes the marginal market share, right? So that's and then this is what I mean by marginal market share. This is the market share that you have at the chosen set when you add product I, and this is the market share at the previously chosen set. So the difference is the marginal, and I'm choosing a set product zi that maximizes the marginal market share. And after that, I'm adding zi to my set. And at the end, I'm returning s of k, which is going to be the final set I'm going to show to the customer. And I think one of the nice things about this greedy algorithm is that it actually builds a solution stage by stage on top of each other. And that's what I mean by the greedy algorithm. So that means that when I'm building a solution stage by stage, I do not go back and revisit my decision. I just build a decision on top of that. And that's kind of the definition of a greedy algorithm in this way. Okay, now what about the online problem? So in the online problem, I have T runs. And in every run T, there is a nature, or call it adversary, that is going to choose a monotone submodular demand function f of t. And note that there's a index like t here, that means that this demand function is time varying. And also this demand function is not unobservable, and that indicates that the decision maker needs to make a decision under uncertainty. So after adversary chooses this demand function, the algorithm is going to choose a set s of t, and then obtains a market share or a reward of f of t at set s of t. And then the algorithm is going to get some feedback afterward. And we focus on two different feedback structure. So full information, which means that algorithm is going to observe the entire function. And then the banded feedback structure, which only means that algorithm only are going to observe f of t at the chosen set s of t. And we have resolved for both of these settings. And of course, banded feedback structure is more challenging. But then to simplify the discussion and today's talk, I'm just going to focus on the full information feedback structure. Okay, so and then this process will continue from every run, adversary chooses something, algorithm chooses set and gets some feedback. And we have that process up to run capital T. Any questions? Okay. If there's no question, so then let me talk about our goal here in this work. So we want to minimize regret with respect to gamma times opt. Gamma is the approximation factor, and opt is going to be the maximum market share that one can get if he or she had the benefit of the hindsight. So this is if I know all this, the demand function f of t in advance, and I get to choose one single set, having this knowledge, this is the best maximum market share that I'm going to be able to obtain. And then I'm calculating the regret by comparing what I'm getting, which is this summation, with gamma times opt. And remember, gamma is the approximation factor. And the reason I have this gamma here is because the offline problem itself is so hard, and I can only get a gamma fraction of the optimal. That's why when it comes to the regret, I'm also focusing on approximate regret, which is a very common notion in the learning literature. Okay. So I think now this is a good time for me to summarize our contribution and main result. I think one of the nice things about this work is that we have a general framework to transform offline greedy algorithm to a low regret online algorithm via Blackwell approachability. And we have a result for both full information studying and bandit feedback structure. And for full information studying, we get O of square root t gamma regret. And then for the bandit feedback structure, we get t to the power of 2 thirds. And for the maximizing monotone set submodular function, which is the running example, for the full information, we can match the best prior bound in the literature. And then for the bandit feedback structure, we improve it. We improve the best prior bound in the literature. But I think I don't want to say that this is kind of the main contribution of this work, because the main contribution is the fact that our framework has a wide range of applications and can be applied to a variety of settings. So here's the list of applications that we try in our paper, and we believe that there are more. So we apply it to product ranking problem, like reserve price optimization, non-monotone set submodular function, non-monotone strong DR submodular function, and non-monotone weak DR submodular function. So and then in all of these cases, either we matches the best prior bound or improve that, or we are the only one that provide a bound for this problem. So let's look at the results. So for the full information setting, we always get, in terms of dependency in T, we get a square root T dependency. And for the bandit, so we get to the power of 2 thirds dependency if our decision set is discrete. For example, for product ranking, so ranking something discrete, we get to the power of 2 thirds. But whenever the decision set is become continuous, in that scenario, I think there are some questions here. Oh, so good question. Are there any lower bounds for these problems? I think as far as I know, for example, I'm not aware of in terms of the dependency on T, I think for full information square root is tight. For the bandit feedback structure, I don't know if it is tight, but then as you can see, this is kind of in majority of cases, we outperform the best known bound in the literature. Thank you for your question. So then for the continuous case, because for example, for reserve price optimization, we need to also do discretization, and discretization is gonna, because of discretization error, our regret bound is gonna get a little bit worse. We get to the power of 4/5. And couple of things that I want to highlight is that if you think about the bandit feedback structure, the bandit feedback structure capture more realistic scenarios, but then you don't see, and it's also more challenging to attack. But we don't see a lot of prior result in the literature, and we are very excited to see that. We are very excited to see the result in the literature, to contribute to the literature by providing bound for the bandit feedback structure. I think for some reason you guys don't see the. Again, I think my video got stuck there, the sharing thing. So, sorry for the comments.
Are you using iPad or?
I'm using iPad.
Yeah, sometimes it freezes.
It freezes. Okay, so Now I think like I also want to talk about related work and kind of to put into context to say how this work contributes to offline to online transformation for NP-hard problems. I think the first and foremost, there's this negative result in the literature saying that for general combinatorial problems, you cannot get sublinear regret. Okay, so and that kind of justifies that why in this work we focus on a class of NP-hard problems that they're amenable to some greedy algorithm with approximation, with constant approximation factor. And there's also like a nice work by Kala and Pampalo 2005 and Dudik 2017 that they provide the algorithm based on follow the perturbed leader, and their approach only works if you can solve the offline problem efficiently. But for our case, this is definitely not the case because we are dealing with NP-hard problems. And for and then there is a great work by Kakade et al. That they show that if the NP-hard is they can handle NP-hard problems, but then for them it's very crucial to have linear rewards, which is again this is not the case even for the maximizing submodular function. There is also a large body of literature on combinatorial learnings, and then for combinatorial learning, I think this literature is pretty mature, but the focus is on linear reward structure, which is not the case for us. So our contribution is that we focus on NP-hard problems with a non-linear reward structure, and then we handle both bandit and full information setting, and we were able to transform offline greedy algorithms to their online counterpart that gets sublinear regret bound. Okay, so now I think like we are getting to the exciting part of the talk, like talking about high-level ideas and presenting the algorithm. Okay, so to explain the high-level ideas, I'm just gonna first revisit the greedy algorithm, present some of the properties of the greedy algorithm, and then based on that, I'm just gonna tell you about the high-level idea and present our algorithm. So if you remember, greedy algorithm has k subproblems, where in subproblem I, we choose a product Zi that maximizes the marginal market share and delta If, and I just introduced new notation just to make everything simpler. Now I'm gonna say, the fact that the greedy algorithm chooses such product is equivalent to this payoff vector to be greater than or equal 0. So let me walk you through this kind of parse this vector for you and look at the first element. So if you look at the first element, this delta F of Zi is the marginal market share at the product that the greedy chooses. And delta F of like 1 is the marginal market share of the product 1. And this should be, of course, greater than or equal 0 because the difference between these two, because the greedy algorithm chooses the product Zi that maximizes the marginal market share. And then the same thing, following the same logic, you can say that all these like elements in this vector should be greater than or equal 0. And then this is equivalent to say that the greedy algorithm chooses the product Zi that maximizes the marginal market share. So, but then there's like a minor issue here. Like, it's nice that I wrote this condition. Later you will see this, why this is nice to write it as this in this form. But there's a minor issue that this vector payoff is not linear in the greedy's decision Zi. And you are gonna find out why this is important. I'm just gonna do it like a simple trick to make it linear. And then after that, talk about another property of the greedy algorithm. So the trick I'm gonna do is that for subproblem I, instead of returning the product Zi, I'm going to return a distribution theta I over the n products that I have. And then what is this distribution? Let's say I only have one product that has the highest marginal market share. Then in that distribution, I just simply put the mass of 1 for that product and put the like 0 for the rest of product. Okay, nothing major, it's the same thing. But then now let me write this vector payoff in terms of theta I. So if I do that, if you think about the yellow part that I highlighted, this is the expected value of the marginal market share at the greedy solution, right? And then again, by the same logic, I know that because greedy algorithm go with a solution that maximizes market share, this vector payoff that I define is going to be again greater than or equal 0. And now why I did that? Because now all of a sudden the vector payoff is linear in the greedy's decision theta I, which is a nice property to have. So now let me also talk about a very nice property of this greedy algorithm. And in fact, I'm going to show you that this greedy algorithm is robust to local errors. So what does it mean? Let's say I have an errorless system. And for every subproblem I and every coordinate j, I manage to make sure that this vector payoff that I have at the solution that I'm returning for every element j is going to be greater than equal 0. Then by non-Husserl's result, we know that if you satisfy that, you are going to get 1 minus 1 over the approximation factor. Okay. So that's what I mean by errorless system. Now, let me add a little bit of error to the system in a sense that instead of theta I, I'm going to replace it with this noisy version, theta I tilde, such that if you look at the payoff vector at the theta I tilde and look at like any j coordinate, this may not be greater than equal 0 as I wish for, but then with a little bit of error, this epsilon with a little bit of like error epsilon is still going to be greater than equal 0. Okay, so that means that I satisfy this condition that I have over there, like kind of approximately with some error. So if I guarantee that I satisfy this condition, so then the greedy algorithm, the solution that the greedy algorithm is going to return is not going to be too far from gamma approximation. It's only going to be epsilon times k away from the gamma approximation, which is a great thing. Because why it is great? Because greedy algorithm beats solution on top of each other, right? So I want to make sure that if in one of the stages I have some error, so the error does not propagate, it just simply adds up together. And it turns out that this greedy algorithm already has that property. In the greedy algorithm, the local errors do not propagate, which is quite nice. But that's not all. In fact, like this greedy algorithm is amazing that in a sense that it's extended robust. So think about like a noisy run of this algorithm over t runs. And let's say that for every run, I have like a noise and I'm returning some noisy version of theta it. And then the noisy version satisfies this inequality that if I add up this vector payoff across all the time periods and look at the coordinate j, with a little bit of error, which is a function of t, this is going to be greater than equal 0. Let's assume that I satisfy this condition, that with a little bit of help, with a little bit of error of t, I satisfy this inequality. Then in that scenario, it is guaranteed that I can satisfy this inequality. And what is this? This is what your algorithm gets. This is a gamma times what the optimal gets. This is kind of the benchmark because S can be any set, including the optimal. And this is kind of the regret part. This how far you are going to be from the benchmark. And at a high level, it means that if the aggregate error over t runs for every coordinate is still small, the algorithm is still going to do well. And in other words, the error again is not going to propagate. If the algorithm satisfies this property, we are going to say that this is extended robust. And not every greedy algorithm is going to have that property, but there, as I'm going to show you, there are many greedy algorithms that has that property. Okay. So now I think this is kind of maybe the most important slide of this talk. I'm going to talk about our high-level idea. So remember, for the offline problem, for every subproblem I return a distribution theta I such that this vector payoff at the theta I and this delta I become greater than equal 0. So that's what I wanted to do. Now for online problem, of course, I don't know the demand function f of t, and still I need to make a decision. What I'm going to do, I'm interested in making sure that in subproblem I return some kind of noisy version of theta I, such that if I'm adding up all this vector payoff and look at coordinate j, with a little bit of help, like of error t, with a little bit of error, I'm going to still be making sure that this is going to be greater than equal 0. Okay. And why this is good? This is good because if I make sure error of t in the order of square root t, by extended robustness property, it is automatic that I'm going to get a square root t gamma regret. Okay, so isn't it amazing? Just by satisfying, making sure that every subproblem I can be done with kind of manageable error in the order of a square root t, by extended robustness, I automatically I'm going to get a square root t gamma regret. And that's kind of the whole idea. But I think there's a main question here: how I'm going to design an algorithm for every subproblem that with the error of t in the order of a square root t. And the answer to that question is the Blackwell approachability. So we are going to use Blackwell approachability to handle that. And let me walk you through the Blackwell approachability. And I'm sure that some of you have seen that. is a two-player zero-sum game with a vector value reward. In every round T, the two players play their actions. P1 obtains some reward, and then P2 obtains the negative of that. Two things that are important: reward is vector valued, and reward vector is going to be by affine. So in the Blackwell game, P1 wants to approach a convex set, and P2 does not want this to happen. And we say a convex set is approachable, meaning that player P1 can get close to that. If there exists for player P1, there is a strategy that no matter what P2 does, the distance between the average vector value reward and set S is going to be less than G of T, where G of T goes to 0 as T goes to infinity. So that means that I'm just, as a player one, I get like closer and closer to set S as T goes to infinity. But of course, not every target set is going to be approachable, and there's simple tests that you can do to see if the set is approachable. I'm not going to bore you with that. But what is important is that if set S is approachable, you can approach it with this rate, 1 over a square root of T. And there are algorithms that allow you to do that, and I'm going to call this algorithm AlgB. This is a Blackwell algorithm that helps you to approach this target approachable set with this rate of 1 over a square root T. Okay, so let me go back to our high-level idea. So remember, I wanted to make sure that error of T is going to be in the order of a square root T. The way I make this happen is that by letting AlgB algorithm, this Blackwell algorithm, handle every subproblem. Okay, so this is the way I'm going to do that. And if this is the case, I need to define some like Blackwell game for every subproblem I, which is doable. Player P1 is going to be the algorithm. Player P2 is going to be the adversary, which returns the delta F. There is a vector payoff vector, which is by affine due to this because of the transformation I did. And that's a reward vector in the Blackwell game. I have a target set, which is the positive order because I want to approach that set, which is approachable. And then if this is the case, the AlgB allows me to approach that set with the rate of 1 over a square root T, which is correspond to error term in the square root T, right? So I think kind of it's magical. So then I would able to, by handling every subproblem with the Blackwell game, I would be able to get error term in the order of a square root T. So let me put everything together. Every subproblem is being handled by a Blackwell game. So I have AlgB1, AlgB2, etc. So after that, they make a decision, pass their decision through the greedy algorithm. And then after I'm getting a feedback, I pass the feedback to them. They obtain themselves. And then I know by this, I know the error term for the AlgB is going to be in the order of a square root T. And then because of the extended robustness, if I have this, consider all the error terms of different AlgB algorithms, these Blackwell algorithms, the total regret bound is going to be K times that because the error does not propagate. And kind of that's the gist of the algorithm. And in fact, we can go beyond assortment planning. If I have a greedy algorithm that is extended robust, meaning that the error does not propagate, and it's Blackwell reducible in the sense that for every subproblem, I can define a Blackwell game with by affine vector payoff and with the approachable target set. In that scenario, I'm going to be able to get a square root T regret. And it turns out that for many of these problems that I talk about product ranking, there are greedy reserve price optimization, non-monotone set submodular function, and for continuous set submodular function, there exists greedy algorithm that has this old property, extended robustness, Blackwell reducible, and then by applying our framework to do these settings, that's the result we are getting. And let me highlight that I think the result that we get for continuous submodular function is quite interesting because for weak DR, there was no result in the literature prior to this work. And then for the strong DR, we significantly outperform the existing one, even in terms of the approximation factor. So we get 1/2 approximation factor, and which is the best thing, and then they get 1/4. Okay, so let me wrap up. So today I talk about transforming offline greedy algorithms to their online counterpart using Blackwell approachability. So we need the greedy algorithm to be extended robust so that when it builds a solution on top of each other, the error does not propagate too much, and that assumption is satisfied by many greedy algorithm. And we want the greedy algorithm to be Blackwell reducible so that for every subproblem, we can define a Blackwell game and let the Blackwell game handle that particular subproblem. For full information studying, we get a square root regret, and for the bandit, we get to the power of 2/3. And we show that our framework is flexible and can be applied to many applications, including product ranking, reserve price optimization, and submodular optimization. We are hoping that people can find more application. And thank you so much for listening to my talk. This is the link to the paper, and this is my email. And I would be delighted to take any questions. Thank you.
Hi.
Thanks, Negin. That was very interesting. I think I have one quick question, or maybe not so quick. I don't know. We have 10-15 minutes for discussion since the other speakers couldn't join for the discussion today. My question is like, can you give a quick insight into like what was greedy? What was the property of greedy algorithm that was crucial here, or is it any algorithm that processes, any offline algorithm that processes one input at a time? Is that like a local kind of, is that
Yeah, I think the
what
main,
you need?
yeah, I think the main thing for the main property, there are a couple of properties that we need. So the main thing is the robustness, because if you think about the greedy algorithm, it has like several like subproblems, but you go from subproblem 1 to 2, etc., and then up to like k. And then for such a greedy algorithm, let's say that in the online learning, you are not going to handle the subproblems accurately. So whatever like decision you make in that subproblem, it might have like some error in a sense that you are not going to exactly follow the thing that you want. In that scenario, you want to make sure that the error you are making in every subproblem does not propagate and become like too large. And that property is not going to be satisfied for every greedy algorithm, for example, for digestra. So you are not going to have this robustness to local errors. So the first like main property we need is robustness to local errors. The other thing is that the like when I was walking you through this vector, oh sorry, like the other way around. So when I walk you through this. So when I walk you through this like high level idea, so one thing I need to have is that for this subproblem, I need to define a Blackwell game for that. And then and that's also important because I need to define some bi-affine vector value payoff. And then I need to make sure that the set that there's a convex set which is approachable. In all of our application, the convex set was just simply positive ortho. So as long as you have these two properties, robustness to local errors and making sure that every subproblems can be handled by a Blackwell game, you can define a Blackwell game for that, and then you can handle the subproblem by a Blackwell algorithm. We can apply our framework. Does it answer your question?
I think like my question is, so these things you need on top of greedy, right? But what if I replace greedy and give you these two properties? So is there something about greedy that you're using? For example, if I have another algorithm, like say some kind of gradient descent or let's say Frank Wolf or something that is local update kind of incremental update kind of method that can be applied online. And you could ensure these two properties. Like, is there something crucial about greedy that you're using here?
Very good question. I think one thing which is, I haven't looked into the details, but I think one thing which is crucial here is that the number of subproblems we need to solve for the offline problem should be also bounded. So I don't know, like, for example, if you apply it to the gradient descent or mirror descent algorithm, if you know exactly how many steps you need to take for the offline setting when you don't have any uncertainty to reach to the point, to the minimum that you want to get in that scenario, yeah, so you can apply our framework. There's nothing special about the greedy algorithm. Any local improvement is going to be good, but then I think we have a dependency on the number of subproblems. So you need to have that. So if you know that the number of subproblems for the offline problem is bounded, yeah, you can apply that as well.
Okay.
But for all of our settings.
So somebody else had a question.
Yeah, go ahead.
Yep. Hi.
No. I was just saying somebody else had a question. Yeah.
Yeah, go ahead.
Okay.
Yeah. I had a query with respect to the federated differentiable online settings, and how can the biases be corrected in them?
Okay, so for federated distributed learning, so every like node is going to make a decision on its own, and then I think that probably our framework can be applied there, and because you are going to have limited steps that you are going through, and then let's say you are going through those steps in a sequential fashion, like for example. There's node 1 make a decision and then node 2, etc. And if you kind of your loss function is robust, like if you, for example, node 1 making a decision and then overall, and then node 2 also make some like maybe a bit like a noisy decision, and overall if that error does not propagate and gets too big, it just adds up. I think that this framework can handle that. That's kind of like my guess.
Okay, thanks.
First, like it depends on the specific problem that you want to also make sure that the problem that every node is solving, this sub problem. Think about like what every node solves as like a one sub problem. So you want to make sure that this sub problem is also Blackwell reducible. You can assign a Blackwell to game to that. So I'm sure there might be like some application on the federated learning that satisfy that, but I haven't looked into that. That's a good question.
Yep. Oh, okay, thanks. I got it.
Any other questions?
Sudeep, do you have a question? Your mic is on.
Oh, no, I was prompted to unmute, so
Okay.
I don't know why that happened. I had no questions. So.
Okay.
I think like you maybe a reply.
Yeah,
Go ahead. I think like Shipra, that you asked some question about the mirror distance. I think this is interesting. One thing I want to say, in all of the application that we consider, the set of sub problems that we need to go over, like in the offline problem, is deterministic and is known ahead of time. And probably like in the mirror distance algorithm, you maybe you know that with high probability, with this number of steps, you are going to kind of converge to the solution that you want, and so. Maybe it needs a little bit of work how to take care of the randomness in the number of steps that you need to make in order to reach your solution. Because for us, every grid algorithm we consider has a fixed number of like sub problems, and then but then potentially can be extended.
Right. Like, I think like, yeah, it will be interesting to see if any incremental algorithm, something that processes one part of the input at a time, not necessarily in a greedy way, but there could be other ways to have an offline incremental algorithm. And yeah.
That's a good question.
Yeah, greedy has this nice structure that it's natural to take it online because, yeah. Right. Do you have any insights on like future directions or things you would like to work on in this?
Yeah, I think like this is an area which is kind of, I think has a lot of potential because the set of papers there is not huge. I think like one thing that I'm interested is that, is there another class of algorithms that not necessarily greedy, but any other wide class of algorithms that we can do the transformation? And also another thing that I'm interested to look at is that, is there like a black box algorithm that just instead of me looking at the details of the algorithm, that's what I did here, right? So I look at the like algorithm, the detail of the algorithm, try to define some payoff vector for that and map it to some Blackwell game. Is there like some way that I can look at this problem in a black box manner that I just give you, like, you give me any algorithm and just I'm gonna tell you that how you can convert it to the online version instead of just looking into details of the algorithm. I think that would be also an interesting direction to pursue. And also, like what you mentioned is also interesting to see that at some point I thought about it, but then I don't, for some reason I kind of stopped. But yeah, I think if you if there are some like gradient based type algorithm that you don't know how long it's going to take you to a stop, but it has some kind of greedy nature because you improve your solution a little bit by a little bit at the time. So then can you say something about the designing of the online algorithm?
Right. If there are no more questions, I think we are towards the end of the session, unless someone has any last questions.
And then I want to say
Okay,
this.
thank you for all the three speakers. And yeah, go ahead.
I just want to say this paper is under review, and I appreciate the feedback. And then because it's easy to improve it. Yeah, if you guys have questions or if you comment, feedback, just feel free to reach out to me, and yeah, would be more than happy to receive those feedback. Thank you.
Yeah, thank you very much. Yeah, it has been a very interesting session, and I'm sure you'll enjoyed it as much as I did. And hope to see you in the next session in half an hour or so.
It's not all Halloween.
Thank you, everybody.